Chapter 3 Linked Lists 1. Review on structures. Structures are aggregate data types built using elements of primitive data types. Structure is defined using the struct keyword, e.g. struct time and hour, int minute, int second. The struct keyword creates a new user-defined data type that is used to declare variables of an aggregate data type. Structure variables are declared like variables of other types. Syntax structure tag variable named, e.g. struct time object, struct time asterisk time up 2. Accessing members of structure variables. The dot operator, to access data members of structure variables. The arrow operator, gt, to access data members of pointer variables pointing to the structure, e.g. print member hour of time object and time of Cuttle time object. Hour, or cuttle time of hour, no time of hour is the same as asterisk time of hour. The parenthesis is required since asterisk has lower precedence than 3. Self-referential structures. Structures can hold pointers to instances of themselves. Struct list char name 10, int count, struct list asterisk next. However, structures cannot contain instances of themselves. 4. The list ADT. A list data structure is sequence of 0 or more elements A1, A2, A3, ANN, length of the list A1, first element AN, last element AI, element at position I if n equals 0, then empty list. Linearly ordered AI precedes AI plus 1, AI follows AI 1 5. Common operations of the list data structures. Print list, print the list. Make empty, create an empty list. Find, locate the position of an object in a list. 34, 12, 52, 16, 12. Find, 52, 3. Insert, insert an object to a list. Insert, x3, 3, 4, 12, 52, x, 16, 12. Remove, delete an element from the list. Remove, 52, 3, 4, 12, x, 16, 12. Find kth, retrieve the element at a certain position. 6. Implementation of an ADT. Choose a data structure to represent the list ADT, e.g. arrays, linked list, etc. Each operation associated with the ADT is implemented by one or more subroutines, functions. 2 standard implementations for the list ADT. Array-based linked list. 7. Array implementation. Need to know the maximum number of elements in the list at the start of the program. Difficult. Waste space if the guess is bad. Adding / deleting an element can take n operations if the list has n elements, as it requires shifting of elements. Accessing / changing an element anywhere takes 1 operations independent of n. Random access. Array implementation. Elements are stored in contiguous array positions. 9. Adding an element. Normally first position, A0, stores the current size of the list. Actual number of elements size plus 1. Adding at the beginning, move all elements 1 position up / behind. Add at position 1, increment the current size by 1. 4. J equals A0 plus 1, JGT1, J, AJ equals AJ1, A1 equals new element, A0 equals A0 plus 1, complexity, O, N, 10. Adding at the end. Add the element at the end. Increment current size by 1, AA0 plus 1 equals new element, A0 equals A0 plus 1, complexity, O, 1, 11. Adding at kth position. Basic steps. Move all elements 1 position behind kth position onwards. Add the element at that position. Increment current size by 1. 4. J equals A0 plus 1, JGTK, J, AJ equals AJ1, AK equals new element, A0 equals A0 plus 1, complexity, O, NK, 12. Deleting an element at the beginning. Deleting at the beginning, move all elements 1 position ahead, decrement the current size by 1. 4. J equals 1, JLTA0, J plus plus, AJ equals AJ plus 1, A0 equals A0-1, complexity, O, N, 13. Deleting at the end. Delete the element at the end. Decrement current size by 1, A0 equals A0-1, complexity, O, 1. 14. Deleting at the kth position. Basic steps: move all elements down one position ahead, k plus 1 th position onwards, decrement the current size by 1. 4. J equals k, JLTA 0 plus 1, J plus plus, AJ equals AJ plus 1, A0 equals A0 dash 1, complexity, O, NK, 15. Accessing an element at the kth position AK, O, 1, operation, 16. Linked lists implementation. ABC head. A linked list is a series of connected nodes. Each node contains at least a piece of data, any type, pointer to the next node in the list head, pointer to the first node. The last node points to NULLA data pointer. Node 17. Array vs linked list. 18. Array. Physically contiguous fixed length access elements by index. Insertion / removal is costly. Linked lists logically contiguous only changeable length access elements by traversal. Insertion / removal is efficient. Defining the data structure for a linked list. The key part of a linked list is a structure, which holds the data for each node. Example: name, address, age or whatever for the items in the list, and, most importantly, a pointer to the next node. Example of a typical node: struct node char name 20, / name of up to 20 letters, int age, float height, / in meters. Node asterisk next, / pointer to next node, struct node asterisk head equals null, 19. Operations on linked lists: inserting a node at the beginning, at the end, at kth position, removing elements from front, from end, from kth position, traversing the list. 20. Adding an element at the beginning. Create a new node. Struct node asterisk nunet equals new node. Fill in the details. Nunet gt name equals / store the value of the name field. Nunet gt age equals / store the value of the age field. Nunet gt height equals / store the value of the height field. Nunet next equals null if the list is empty to start with. If head equals null, head equals nunet, else pointer from the nunet points to head. Nunet next equals header, header equals nunet. 21. Adding an element at the end. Create a new node. Pointer from the last node points to new node. Create nunet last dot next equals nunet. How do we find the last node? So, step through the list until it finds the last node. Last equals head, / we know this is not null list, not empty. While last gtnxt equals null, last equals last text, / move to next link in chain 22. Adding an element at the end. Void add underscore node underscore at underscore end, node asterisk temp 2, / temporary pointers / reserve space for new node and fill it with data. Temp equals new node. Cuddle, please enter the name of the person. Sync temp name. Cuddle, please enter the age of the person. Sync temp age. Cuddle, please enter the height of the person. Sync temp feet. Temp gtnxt equals null, / set up link to this node if head equals null, head equals temp, else temp2 equals head, / we know this is not null list, not empty. While temp2 gtnxt equals null, temp2 equals temp2 gtnxt, / move to next link in chain. Temp2 gtnxt equals temp, / add node at end. Complexity, O, N, 23. Displaying the list of nodes. Method 1. Set a temporary pointer to point to the head 2. If the pointer points to null, display the message end of list and stop. 3. Otherwise, display the details of the node pointed to by the head pointer. 4. Make the temporary pointer point to the same thing as the NXT pointer of the node it is currently indicating. 5. Jump back to step 2. 24. Displaying the list of nodes. Temp equals head. Do if temp equals null, cuddle end of list lt and l, / display details for what temp points to. Cuddle name, lt temp name lt and l, cuddle age, lt temp dig lt and l, cuddle height, lt temp feet lt and l, cuddle and l, / blank line / move to next node, if present, temp equals temp gtnxt, while temp, equals null, 25. Navigating through the list necessary when you want to insert or delete a node from somewhere inside the list. Node asterisk current, current equals head, if current GTNXT equals null, cuddle you are at the end of the list LT and L, else current equals current GTNXT, moving the current pointer back one step is a little harder. 26. Deleting a node. Basic steps. Find the desirable node to be deleted. Release the memory occupied by the found node. Set the pointer of the predecessor of the found node to the successor of the found node. When it comes to delete nodes, we have three choices: delete a node from the start of the list, delete one from the end of the list, or delete at that position. 27. Deleting the first node in the linked list. Temp equals head, / make the temp pointer / point to the head pointer. Head equals head GTNXT, / second node in chain. Delete temp, here is the function that deletes a node from the head. Void delete _ start _ node asterisk temp equals head equals head GTNXT, delete temp. 28. Deleting the last node. Steps. 1. Look at the head pointer. If it is null, then the list is empty, so print out a no nodes to delete message. 2. Make temp1 point to whatever the head pointer is pointing to. Temp1 equals head. 3. If the next pointer of what temp1 indicates is null, then we've found the last node of the list, so jump to step 7, otherwise go to the next step. If temp1 next equals null. 4. Make another pointer, temp2, point to the current node in the list. Temp2 equals temp1 5. Make temp1 point to the next item in the list. Temp1 equals temp1 next 6. Go to step 3. 7. Delete the node pointed by temp1. Delete temp1 8. Mark the next pointer of the node pointed by temp2 as null. It is the new last node. Temp2 next equals null. 29. Delete node from the end of the list. Void delete _ end _ node asterisk temp1 asterisk temp2. If head equals null, cuddle the list is empty, LT and L, else temp1 equals head. If temp1 GTNXT equals null, delete temp1, head equals null, else while temp1 GTNXT equals null, temp2 equals temp1, temp1 equals temp1 GTNXT, delete temp1, temp2 GTNXT equals null, / delete. End of node. 30. Variations of linked lists. Circular linked lists. The last node points to the first node of the list ABC head. How do we know when we have finished traversing the list? Tip: check if the pointer of the current node is equal to the head. 31. Variations of linked lists. Doubly linked lists. Each node points to not only successor but the predecessor. There are two NULL at the first and last nodes in the list. Advantage: given a node, it is easy to visit its predecessor. Convenient to traverse lists backwards. ABC head. 32. Array versus linked lists. Linked lists are more complex to code and manage than arrays, but they have some distinct advantages. Dynamic: a linked list can easily grow and shrink in size. We don't need to know how many nodes will be in the list. They are created in memory as needed. In contrast, the size of a C++ array is fixed at compilation time. Easy and fast insertions and deletions. To insert or delete an element in an array, we need to copy two temporary variables to make room for new elements or close the gap caused by deleted elements. With a linked list, no need to move other nodes. Only need to reset some pointers. 33. End of chapter 334.